Do you have some problems to do?
No, they were mostly all just like constructions.
Okay. Well, let's talk about what an end center is. Hold on. If I inscribe a triangle inside of a circle, and I take my perpendicular bisectors of each side. In other words, if I start there where that side's equal to that side, and I draw a perpendicular, that's a right angle. I do the same thing with every side, and I draw a perpendicular. That's a right angle. And I do the same thing down there, and the perpendicular is supposed to be a perpendicular. Produces an interesting place. The unique property of that center is that it is equidistant from each vertex. In other words, this distance is equal to that distance, which is equal to that distance, which is one thing that allows you to inscribe that triangle inside of a circle, is that whatever the center you come up with, which is the center of the circle also, will be equidistant from the vertexes of the triangle. And the only way to find this center is to bisect each side with perpendicular lines like that. Now, you don't always have the circle outside of it. This is just a way that I use to remember what the end center is. In other words, the end center is what you get, or you end up with a triangle that is inscribed. You know the difference between inscribed and circumscribed, right?
Kind of.
Okay, well, let's go talk about circumscribed. If I want this situation where I could have a circle that is circumscribed by the triangle. Remember, in this one over here, the triangle was inscribed in the circle. Well, this triangle is going to circumscribe the circle, and it's going to be called the circumcenter because of that. And how you get the circumcenter is if you start with each vertex and you do a angle bisector. In other words, where that angle is equal to that angle. And you do that from all three vertexes. Interestingly enough, they all go to the same point. And that point is called the circumcenter. Now, the value, that's a different center of a triangle than this one over here. And what is true here is that it is equidistant from the sides. In other words, that distance is the same as that distance is the same as that distance. Hence, I could draw a circle inside the triangle. Okay? Now, let's talk about these two situations, because one really easy way to remember it is that the one on the left, you begin by starting from the sides and you produce a point that is equidistant from the vertexes. The one on the right, you start from the vertexes and you produce a point that is equidistant from the sides. In other words, they kind of work in opposite manners. If you want a triangle that can be inscribed inside of a circle, then you need the center of that triangle to be equidistant from the vertexes. But if you want a triangle that can have a circle inscribed inside of it, then you want a center that's equidistant from the sides of the triangle when measured on a perpendicular. And I mean, one thing that might not seem obvious to the average person is where's the center of a triangle? You know, if I draw a triangle like that, where's the center? Is it there? Is it there? Is it there? There is no acceptable center. There's the end center and there's the circumcenter. They're in different places of the same triangle. And then there's two more. There's the Ortho center and the Centroid. Although we'll hold off on that for a moment. Although I do want to mention one thing. There is a true center to all triangles. And that's really the centroid, or the center of mass. And what I mean by that is if you had a triangle that was a piece of cardboard 1 inch thick throughout, you with me?
Mm-hmm.
And you were to take a pencil and try to balance that triangle on the center of that pencil. You getting my picture? Think of,
Yeah.
okay, that's the centroid. That is the center of mass. In other words, if that was your problem, and that frequently is a problem where you want to find the center of mass of a triangle, the thing is that that's half of a physics problem and half of a math problem. Well, you get the center of mass, or the centroid is what it's called, from a different technique. You do medians. You start from the vertex and you go to the center of the other side. So I start from the vertex and I go to the center of the other side. Start from that vertex, go to the center of that side. Those all intersect at the same point, and that's your centroid. That's probably the most important one. Certainly from a physics point of view, that's the most important one. And as long as we're talking about it, let's talk about the ortho center. That's the fourth one. Well, you construct an ortho, and one way I kind of remember the name for ortho center is it can be outside of the center of the triangle. And what you do is you take each vertex and you drop a perpendicular to the other side. In other words, there's that perpendicular. There's this perpendicular. And this perpendicular goes down there, and you have a center that's outside the triangle.
Mm-hmm.
But that's all you do is you start with one vertex and you drop a line that's perpendicular to this side here. And you extend it as far as you have to. I didn't leave quite enough room on this page. Here, let me draw it a little bit better. Redraw this here. In other words, I purposefully did an obtuse triangle because when you have an obtuse triangle, the orthocenter frequently ends up outside of the triangle. Okay? So if I'm going to draw a perpendicular to the other side, but I'm going to extend it all the way down here, and now I'm going to go to this vertex and drop a perpendicular to the other side like that. I still didn't draw it big enough. And in this one, I'm going to draw a perpendicular to the side, this side here, its other side. And you'll notice that they all connect way outside the triangle.
Mm-hmm.
And that's the orthocenter. If I had a more traditional triangle like this, then the orthocenter would be, I'm dropping a perpendicular to that side, I'm dropping a perpendicular to that side, and I'm dropping a perpendicular to that side. So in this case, it's inside the triangle. So if you have a typical triangle, the orthocenter will be inside the triangle. If you have an obtuse, it'll frequently be outside the triangle. It's the only one that can be outside the triangle. The other three are always inside the triangle. And there are properties to some of these that we haven't talked about. The most important property of the center, this one here, is that it is equidistant from the vertexes, which allows you to draw a circle around the triangle and have all three vertexes on the edge of the circle.
Mm-hmm.
The most important property of the circumcenter is that the center you come up with is equidistant from the sides of the triangle, allowing you to draw a circle inside the triangle. Notice that these three lines are all going to be radiuses, and if they're equidistant, then we're going to have a perfect circle in there. There's a few other properties to centroid. I don't know how soon you'll get to that and whether we want to go that far today or not. Usually my geometry students will spend like a week on the incenter and the circumcenter, and then maybe another week on the centroid and the orthocenter, and talking about the properties of each. So if you're just beginning this, how long have you had any of that? Is all of this new to you, or have you had a day or two?
We started on Tuesday, and we've just been doing constructions.
Okay, with your compass and protractor, mainly the compass?
We've been doing like constructions and drawings.
Okay, but
both of them.
instructions like how to figure out how to make a line that's perpendicular with another line?
Like how to make an orthocenter, like how to make an altitude and like a median.
Oh, okay. So you are doing some of this. Oh, and you're doing it by construction. Okay, I get.
Yeah.
Yeah, I guess you would have to do that first, huh? In other words,
Mm-hmm.
you have to learn how to use the compass, how to bisect an angle with a compass, and how to draw a perpendicular, and both of those tools are required to do an incenter and a circumcenter. In other words, you have to be able to draw a perpendicular to do each of those three black lines in the incenter, and you have to be able to bisect an angle to be able to do the circumcenter.
Mm-hmm.
So yeah, I don't ever think about constructing it. I just know that if that's a bisector and if that's a perpendicular line, you end up with all three of them crossing, which is kind of amazing when you think about it, that all three of them would meet at the center in all four of these cases.
Mm-hmm.
Who knew triangles had such magical properties almost? Okay. Well, one other thing. Have you gotten to centroid and orthocenters yet?
Yeah.
Okay. Let's talk about some of the properties of a centroid. Let me redraw it a little bit bigger because this one has more algebraic properties. I'm going to draw it kind of like this. Now, to get the centroid, you do a combination of the first two. Notice that the first one was bisecting a side and drawing a perpendicular, and the second one was bisecting a vertex angle and just drawing it. Well, to get the centroid, you do the median. In other words, you start from the vertex. This is called median, and it produces the centroid, which again is the center of mass. So to me, this is the most important center. And you connect it to the middle of the other side, like this. Yeah, let's do this in red. And I'm going to go this side to the middle of that side. And I'm going to go from that vertex to the middle of that side. And this centroid actually has a very interesting property. And that is that if, let's see, this distance, how can I say this, x and y, x is equal to 2/3 of x plus y. And same thing with each line. In other words, if this is A and this is B, then A is equal to 2/3 of the total distance of the line, A plus B. And likewise, if this is D and this is E, then E is equal to 2/3 of D plus E. So this is the only in-center that I know of that has these algebraic properties like this, which probably has something to do with why it's the best one, why it ends up being the center of mass. In other words, if I could take that shape and put a pencil on the red center and, you know, orient it trying to balance the triangle on top of the pencil, that's where you would try to balance it, is in the centroid of paper. As long as it was a piece of cardboard that was the same thickness throughout, which is called a planar. It's actually a mathematical term where you have a uniform thickness of like a piece of cardboard, and how you find the center of that planar shape. And it's always going to be balancing stuff, but it's not always triangles. In other words, I could have a shape like this, and that shape has some place and somewhere in there where if I tried balancing this shape on top of a pencil, it would be the perfect balance point. And so the word centroid actually involves all kinds of shapes, not just triangles. But at the moment, you're just going to be learning about it with triangles. And incidentally, this problem is a calculus problem as to how to find the true center of mass of a complicated curved shape like this. There's a way to do it using calculus. But hold on. Oops. Okay, that's kind of the basics of bisectors of a triangle. I'm trying to think if there's anything else that is algebraic. Hold on, let me look through the book here. Yeah, points of concurrency is what this subject matter is called. Points of concurrence. There's 4 of them. And yeah, the last 2 are called medians and altitudes. And the altitude is where you drop from the vertex perpendicularly towards the other side. Okay, and the altitude is what produces the orthocenter, which I kind of remember as being the outside center. You know, ortho, outside. It's the so anything you can use to memorize stuff is useful. Let me see what they say about altitude. The only thing they say about altitudes which produce the orthocenter is that they will intersect at some point. There is no algebraic equalities that the altitudes produce. You've learned about mid-segment theorem? Have you?
Yeah.
In other words, yeah, it seems like we did mid-segment stuff last time. Anytime you take that, make it parallel to the bottom one, this, if this is x, this is 1/2 x, as long as it bisects the sides. Now let's talk about a couple of things of triangles. This is something that, oddly enough, most of my geometry students do not cover. There is a standard theorem that you will need to know for the SAT test and the ACT test that says any side of a triangle has to be less than the sum of the other 2. And the converse of that. Not only has to be less than the sum of the other 2, but it has to be also greater than the difference of the other 2. So if I were to take a 2, 3, 5 triangle, can that be a triangle?
No.
Correct. In fact, none of the sides follow this formula because 5 is not less than 5, and it's definitely less than or greater than. It's not less than or equal. There's no way you can draw a triangle with these dimensions. However, if I make that 4, now if you analyze each side, 4 is less than 2 plus 3. It's also greater than 3 minus 2. 2 is less than 3 plus 4, and it's greater than 4 minus 3. And 3 is less than 2 plus 4, and it's greater than 4 minus 2. So this is one of the more fundamental theorems about triangles that not everybody learns who takes geometry. The thing that's special about it is you really only have to memorize that top part and realize that there's a second part that's the opposite. In other words, if any side is less than the sum of the other two or greater than the difference of the other two. Notice how they are opposite in both respects. So this kind of makes it a little easier to memorize. There's another theorem, our last 3 minutes, that says the longest side of a triangle is always opposite the biggest angle, and the shortest side is always opposite the smallest angle. So rank these sides by length, going from smallest to largest. What's the smallest side?
Y.
What's the next smallest side?
Z.
And finally, Z has to be less than X. Okay, that's something that you might have inherently figured out, that the sides of a triangle have to be in the same order as the sides or the size of their angles, their opposite angles.
Mm-hmm.
All right. Well, as much as I can make up in a half hour. Bring to the table. Hopefully next week you'll have some material that we'll be able to cover. I always prefer that rather than me bringing it to, because I never know exactly what you're going over in class.
Mm-hmm.
Not all classes are the same. Not all schools are the same. So I hate to go over what I think you're going to go over in class, because you may not be going over some of this stuff in class. So it's always better if you bring the problems to the session.
Yeah,
but
I'll probably.
This was a good primer on circumcenters.
Mm-hmm.
All right, Allie, I'll talk to you next Wednesday at 4.
Yes.
Okay.
Thank you.
Have a good week. Bye-bye.
Bye.